recording what I'm sharing. Okay, so this is learning assignment, and if I slip up and call it lecture assignment 3, then it's because that's what I used to call them, and I'm trying to think more about how it's built for you to learn and self-teach, and we're not lecturing, so I just switched to calling it a learning assignment. When I go through this assignment, what I'm looking for is, could you use the periodic table and what you learned going through the PowerPoint to figure out how many valence electrons each of these elements has in one atom of that element? Would it be helpful if I went over a couple of these so you knew for sure how to do it? Yes? No?
Sure.
I got kind of mixed up when it went into like number 6 through 12, or especially number 12. So I'm hoping that there's enough time that we could talk about number 12 a little bit.
Yeah, let's spot check just the first couple here. And what I'm going to do is split my screen. If it'll, no, don't make it big. I'm talking to my computer. You know how when you pull things into the corner, it will make everything huge, and I'm trying to avoid that. All right, I believe I have a periodic table saved. An ugly one, but nonetheless. Nope.
I just had a quick question.
Sure.
So if we're going over 2.1 now, I'm just wondering when and how we could ask maybe more specific questions that we're having with the next part, like this week. Like I'm going over 2.3, I think, and I just have more specific questions about the textbook, and I'm wondering how we can like ask that to you without blowing up your inbox, I guess.
Well, what I wanted to do was do another Zoom tomorrow, and I've also thought about screencasting, but that would be me recording without anybody there. And I just want to grab a periodic table here. And I'm just worried about overloading you guys. And so I thought we need to catch up for the stuff that's for tonight. And then 2.2 is water and pH, and 2.3. So I could do that Tuesday, I could do it Thursday, I could do both. And I could just say, hey, I'll do 2.2 and 2.3 on Tuesday, and then again on Thursday, and whoever shows up on whichever day. So
my only problem is I can only make it to these, like this specific time, just because I signed up for the class because I work till 5. So I have it's hard for me to get to like the 3 or 4 because I'm still at work. So
okay, so you might have to email me, or we might have to try to plan like a 20-minute one-on-one Zoom or something like that. So when everybody else leaves at the end tonight and I stop recording, stick around for a minute and we'll talk about it, okay?
Okay.
All right, so here's my periodic table, and I of course chose one that maybe is, I want one that's a better focus. That's just trying to get one. That one seemed kind of blurry. All right, let me have it. Oh, well, okay, that was worse. It just has to do with what size it is. Okay, but it'll work for me to point out. So when I look at these, remember the valence shell is the outside shell. So as soon as an element has more than 2 electrons, its electrons are going to be orbiting the nucleus in more than one shell. And so the valence shell is the outermost shell. And if I look at, say, Mg for magnesium, then what I want to do is find magnesium over here on the periodic table, and it's in the second column, so I know that it has a total of, if I'm going this way and I count to the right, everything in this column would have 1 valence electron, and everything in column 2 would have 2 valence electrons. So Mg has 2, and so what do I do for magnesium to draw the electron dot symbols? I just put 2 little dots right above magnesium, and that's the electron dot symbols. And if I were to look at chlorine as a second example, then it's over here in the 7th column, And so, and its atomic number is 17, so it has 2 electrons in the first shell and 8 electrons in the second, and that makes 10. And then what's left? 7. It has 7 electrons in the valence shell. So how many dots would I draw around chlorine? I would draw 7 dots, and I would draw them in pairs. So it would be 2, 4, 6, and then 1. This is where I really want a whiteboard so I could show you this just like that. Okay. Is that okay with how to do the dot structure? Pretty straightforward? Okay. And then it shows you the example here, and then it shows you, hey, what happens when I'm going to bond these guys together? So 2 chlorine ion atoms, they each have 1 spot missing in their valence shell. So in order to be full or to be stable, they're going to share those, and those 2 dots that were singular, now we draw in between. And so they're being shared. So those electrons are spending relatively equal time orbiting this nucleus and this nucleus. And so how do I show those 2 shared ones? I draw a line, and so the line represents a covalent bond or a pair of shared electrons. That's different from an ionic bond where 1 electron gets transferred. And then this next example shows you how we have lone pairs in oxygen. And then each oxygen atom here with the hydrogen is sharing an electron, because oxygen has 6 valence electrons. And so it has 2, 4, and then 5 and 6, and then each hydrogen has 1. And so we show the one that the oxygen has and the one that the hydrogen has with a line here. And then again, the same thing with the other one. So H2O, there's a total of 8 electrons being, in that valence shell for the molecule. And we call it, we don't call this one a double covalent bond. These are single bonds right here, but when 2 oxygen atoms share electrons in a molecule, because they're sharing a total of 4, we call it a double covalent bond. And then number 4 just says, hey, look at the periodic table, figure out how many electrons there are, and then decide how many there would need to be for the valence shell to be full, which means satisfy the octet rule. So if I look at Br, which is bromine, and I find it here, it's in column 7. So I know that it needs, to get over here to, basically to be full, it would need 1 more. And this last column is called the inert or noble gases, and that's because their valence shells are full and there's no room for any more electrons. So how many would bromine need to step up 1 and be full? It would need 1. So I would just write 1 right here for bromine. Then I look at nitrogen, which is N, and I say, okay, here it is, and it's in it's in column 5. We're ignoring the transitional elements in the middle, and we're counting 1, 2, 3, 4, 5. And so to get to where it's stable, how many more columns does it have to jump? 1, 2, 3. So how many valence electrons does it still need? It would need 3. And so that's how you fill in 4. And then number 5, with the Lewis dot structures, it's basically asking you to do what is here and show how that would be drawn. This one, and by the way, since you're at home and you can Google stuff, you could always type in NH3 and Lewis dot structure, and I'm sure you'd probably come up with an image and it would show you exactly what you're supposed to have. That's not cheating right now, okay? To look up something because you can't figure it out and to work backwards and to go, aha, I see, now I get it. I'm totally fine with that. You have open resource everything right now, okay? Just don't plop something in an assignment and copy and paste it and say it was yours because you want to avoid plagiarism, right? Good so far? Okay, so now I look at number 6 and it says, how many lone pairs are present on each nitrogen atom in the N2 molecule? So I have to look at nitrogen, and this is where I want a whiteboard so bad. And each nitrogen is going to have 5, right? And valence electrons. So if I have 2 nitrogens side by side, how many of those do they each have to share in order to get to a total of 8? Well, 2 plus, they each have 5, so they each need 3 more. So each nitrogen has to share 3 electrons. So it has 5, it shares 3 of those and gets a shared other 3, so that the 5 plus the 3 is the 8. So if we're sharing 3, how many electrons are left that aren't being shared? Just 2. And so the 2 is a lone pair. So that's how you figure out lone pairs. Whatever electrons are being shared, those are making a covalent bond, and the electrons that are left that aren't being shared, those are what we call a lone pair. And every set of 2 electrons would be a lone pair. Okay, and then number 10, let's see, just jumping ahead here, it says what type of bond forms between the C and the O in number 5E above. So CH2O, and so if you were to draw this out, carbon is in the 4th column, and it has 4 valence electrons, which means it has 4 spaces. And so the carbon is actually going to be bonded and share with each hydrogen, then it's also going to be bonded to the oxygen. And because carbon has to form 4 bonds, each hydrogen counts as 1, but the oxygen, remember, it has 2 spaces to fill. So we're going to have a double covalent bond between the carbon and the oxygen. And this is where I'm going to use Google to help me. And I'm going to type in CH2O image. And
I had another question about that.
yeah, but hold on one second. Do you see this right here with the carbon in the middle? And then it's sharing 1 electron and the hydrogen sharing 1. So that's why it's a line to show that they're being shared. Another line here to show that 2 are being shared. So 2, 4, and then carbon has 2 left, so it can share 2 spots, and then the oxygen is sharing. So 2, 4, 6, 8. And for the oxygen, 2, 4, 6, 8. And that's how they both satisfy the octet rule. All right, so what was the question?
Is there only one way to form every molecule? Like for F, for example, I did have to Google some of these to like look at the, like you were doing, but for that one, I tried to do it myself first, and I I thought I had done it, and then I Googled it, and it was a different way.
It was a different one.
Yeah.
So most of these simple guys, they only have one way. There's going to be an atom that is more central, like carbon having 4 spaces, 4 spots, and fluorine only having 1 that it needs space to fill. So each of those fluorine are going to share 1 electron with the carbon. And so with CF4 would be a carbon in the middle with a single covalent bond to a fluorine in each of 4 spots. And if I Google that, CF4, then you can see what that looks like, okay? Where we've got those 3 lone pairs, and fluorine has a valence of 7, and so it's sharing the 1 with the carbon. And here's carbon's valence of 4, but they're all being shared so that the octet rule is satisfied. But when you get, and this is where it's a little preview of sugars, C2H6O, the reason carbon-based life is so elaborate or diversified, and there are lots of carbon-based molecules, is because there's a lot of variety in how carbon, with its 4 valence electrons, can bond to hydrogen and oxygen. And you will see, what do you need, baby? Oh yeah? This is my 1-year-old right here. So the carbon is really versatile, and it can create ring structures, and it can create chains, and it can create branching chains. And that's why carbon, hydrogen, and oxygen are really the 3 most common elements in lipids, in sugars, and in proteins. And so don't worry, I'm not going to throw something else other than these that are exactly on the learning assignment on the test. It's not my goal to trick you. It's not my goal to make you redo the whole year of chemistry that you were technically supposed to have had as a prerequisite for coming in here. It's do you understand valence electrons? Do you understand how to do the Lewis dot structure? And can you take a few of these elements and put them together in relatively simple, I know you're saying haha, relatively simple, but if you took organic chemistry, you'd know what I was talking about. Relatively simple molecules, and see how they're covalently bonded and how there are electron pairs and single, double, or triple covalent bonds.
Can I ask one quick question on that a little bit? So before you said like nitrogen would have one lone pair, and then so fluorine has 3 lone pairs there. Does that mean it will only ever make one bond?
Yeah, because if we look at the periodic table and I pull that back up, can you see how fluorine is in column 7?
7, right.
It has 7 valence electrons, and because of the row that it is in, it only has 1 spot. So it's only ever going to fill 1 space. And so the periodic table is basically a tool to tell you what the valence of a particular atom would be based on where it's placed in the table. Now, as we get like further and further down, because those valence shells are further from the nucleus, they actually hold more than 8 electrons. But we're doing chemistry for dummies. Because this is a biology class and we're only going as far as it's relevant for biological molecules and trying to understand how these atoms can combine together to make ionic bonds or covalent bonds, and that that's relevant to, carbon-based life. Go have some fun with chemistry and take a few classes if you want to if you want to stress out about more of that, right?
Yeah.
Is that helpful?
Yes, it is. Thank you.
Okay, so somebody said number 12, and I know I emailed a few people. I condensed or shortened this assignment, and I basically just had an oopsie where it shouldn't, and I fixed it, but it was too late for like a lot of you. It referred to a number 19, and that was just a mistake because I deleted a whole bunch of internal things, and I corrected the numbering down the left side and missed the internal. Oh, since I deleted, there's a reference in here. And that's where what happened with 12. And so I'm going to move this up here because it's a little bit behind. She's eating crackers. Okay, so maybe.
So how many covalent bonds should I expect sulfur to form? Because when you start Googling it, it gets more and more complicated. So I had my initial answer, but then I started going down a rabbit hole.
So just without getting complex, if you look at the periodic table, sulfur is in the 6th column. And so it has 2 spaces. So I would expect that because it has 6 electrons in its valence shell, that 4 of those would form the lone pairs. They wouldn't covalently bond, and that the remaining 2, because each of those would have an empty spot, would be able to form a covalent bond. And so would be expected to have 2 lone pairs and 2 covalent bonds.
Okay.
And then
that
if we
coincides,
that just is based on where it's located. So find P in the table. So potassium, it's in column 5. So it has 5 valence electrons and it has 3 spots. So three of its valence electrons are going to share, and that uses up 3, leaving 2. So those 2 unshared ones are going to be a lone pair. So it would have 1 pair and 3 covalent bonds. And nitrogen right above it, nitrogen's in the same group, so it's going to behave similarly and it's going to do the same thing. Oxygen in the same column with sulfur, so what's it going to do?
2 and 2.
Yeah, exactly. And carbon, carbon's in row 4, so carbon is actually going to, because it's got 4 individual electrons all with a spot next to them, it's probably going to form 4 covalent bonds. And that's one of the reasons why we have carbon-based life, because carbon is so versatile. And you may have seen in like sci-fi movies, they may talk about silicon-based life. And that's, look at where silicon is, Si. It's right below carbon in the periodic table. And so that's where the sci-fi idea comes from, that, gee, silicon's versatile. It could do the same thing as carbon. Okay, so we good with number 3 here? And I can close it? Okay.